travelers in a three-way switch circuit do not inherently require a neutral conductor. They function to carry current between the switches, which are connected in parallel to the lighting fixtures. The primary concern raised is electromagnetic interference, often abbreviated as EMI. EMI arises in electrical systems where magnetic fields generated by current-carrying conductors can induce voltages in nearby conductors. However, in the scenario of three-way switch circuits, the EMI produced by the current passing through the travelers is generally considered negligible. This is primarily because the traveler conductors are typically short in length and are installed in close proximity to other conductors. This proximity helps to mitigate the strength of the magnetic field. Also, fluorescent fixtures operating at 120 volts imply that the current flowing through the travelers is relatively low, further minimizing the potential for EMI. Switch loops, which represent wiring configurations that connect switches and fixtures in a parallel arrangement, do not necessitate neutrals because their function differs from providing a direct current path to the fixtures. In a typical three-way switch circuit, the neutral conductor is directly connected to the fixtures. This direct connection furnishes the requisite path for the current to flow. Based on typical electrical practices and principles, the absence of a neutral conductor within the traveler conduit is unlikely to present a significant safety risk or EMI concern. However, it is always prudent to seek the advice of a certified electrician to evaluate the particular installation and to confirm adherence to relevant electrical codes and standards. Now let's delve deeper into the reasons why a neutral wire is generally not required for travelers in a three-way switch setup and explore related concepts in more detail. Firstly, understanding the fundamental operation of a three-way switch circuit is paramount. In such a circuit, two three-way switches control a single lighting fixture or a group of fixtures from two different locations. Each three-way switch has a common terminal, which is connected to either the power source or the lighting fixture, and two traveler terminals. Traveler terminals on each switch are connected to each other via the traveler wires. The key to the operation lies in the switching action. When the position of one switch changes, it alters the path of the current flowing through the traveler wires, which in turn affects the state of the lighting fixture. If the fixture was on, it turns off, and vice versa. Secondly, the role of the neutral wire in an electrical circuit needs clarification. The neutral wire provides a return path for the current to the source, completing the electrical circuit. It is typically grounded to the service panel, ensuring that it is at or near 0 volts potential relative to ground. In a standard 120 volt circuit, the hot wire carries the current to the load, and the neutral wire returns the current to the source. However, in a three-way switch circuit, the travelers do not directly supply power to the load. They simply act as a pathway for the current to be redirected based on the switch positions. The neutral wire is connected directly to the lighting fixture, providing the necessary return path for the current when the fixture is energized. Thirdly, electromagnetic fields and electromagnetic interference merit closer attention. Any current-carrying conductor generates a magnetic field around it. The strength of this magnetic field is proportional to the magnitude of the current flowing through the conductor. When this magnetic field interacts with other conductors, it can induce a voltage in them, leading to EMI. EMI can disrupt the operation of sensitive electronic equipment and can also cause other undesirable effects. However, as previously mentioned, the current flowing through the traveler wires in a three-way switch circuit is typically relatively low, and the conductors are usually run in close proximity to each other. This reduces the strength of the magnetic field and minimizes the potential for EMI. Fourthly, switch loops are often mentioned in the context of electrical wiring. A switch loop is a wiring configuration where a switch is used to control a lighting fixture from a single location. In a switch loop, the hot wire is run to the switch, and another wire, called the switch leg, is run from the switch to the lighting fixture. When the switch is closed, it completes the circuit and the fixture turns on. When the switch is open, it breaks the circuit and the fixture turns off. Like three-way switch circuits, switch loops do not require a neutral wire at the switch because the switch simply interrupts the flow of current to the fixture. The neutral wire is connected directly to the fixture, providing the return path for the current. Fifthly, addressing concerns about safety and code compliance is essential. While the absence of a neutral wire in the traveler conduit may not pose a significant safety risk or EMI concern under normal circumstances, it is crucial to ensure that the installation complies with all applicable electrical codes and standards. The National Electrical Code, often abbreviated as NEC, provides comprehensive guidelines for safe and effective electrical installations. It is important to consult the NEC and any local electrical codes to determine the specific requirements for wiring three-way switch circuits. Furthermore, it is always advisable to have a qualified electrician inspect the installation to ensure that it is safe and compliant. Sixthly, considering alternative wiring methods can be beneficial in certain situations. Although a two-wire cable is commonly used for travelers in three-way switch circuits, there are situations where using a three-wire cable may be advantageous. For example, if there is a need to provide power to a device at one of the switch locations, a three-wire cable can be used to carry both the travelers and the neutral wire. This can eliminate the need to run a separate cable for the neutral wire. Also, in some cases, using a three-wire cable may provide additional protection against EMI. Seventhly, specific installations may necessitate different considerations. The information provided is general in nature and may not apply to all situations. Each electrical installation is unique and may have its own specific requirements. Factors such as the length of the traveler wires, the type of lighting fixtures being controlled, and the presence of other electrical equipment in the vicinity can all affect the need for a neutral wire. Therefore, it is important to carefully evaluate each installation and to consult with a qualified electrician to determine the best wiring method. Eighthly, the importance of proper grounding should be emphasized. Grounding is a critical safety feature in electrical systems. It provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse in to energize the circuit in the event of a ground fault. In a three-way switch circuit, the grounding conductor should be connected to the metal boxes that house the switches and to the metal frame of the lighting fixture. This helps to protect against electric shock in the event of a fault. Ninthly, addressing the specific scenario described is necessary. In the described scenario, a two-wire NC cable was run between the three-way switches for the travelers. While this is a common practice, it is important to ensure that the installation complies with all applicable electrical codes and standards. As previously mentioned, the absence of a neutral wire in the traveler conduit may not pose a significant safety risk or EMI concern under normal circumstances. However, it is still advisable to consult with a qualified electrician to evaluate the installation and to verify its compliance with electrical codes. Tenthly, the importance of ongoing maintenance and inspection should not be overlooked. The electrical systems should be inspected regularly to ensure that they are in good working order and that they are not posing any safety hazards. Three-way switch circuits are no exception. The switches should be checked to ensure that they are operating properly and that the wires are securely connected. The wiring should also be inspected for any signs of damage or deterioration. If any problems are found, they should be corrected promptly by a qualified electrician. Now, let's further elaborate on some of the key concepts discussed earlier, providing additional details and explanations. Firstly, let's revisit the topic of electromagnetic interference, EMI, and its potential impact on electrical circuits. As previously mentioned, EMI is a phenomenon that occurs when the magnetic field generated by a current-carrying conductor induces a voltage in a nearby conductor. This induced voltage can interfere with the operation of sensitive electronic equipment, causing malfunctions or even damage. The severity of EMI depends on several factors, including the strength of the magnetic field, the distance between the conductors, and the sensitivity of the equipment being affected. In the context of three-way switch circuits, the potential for EMI is generally low due to the relatively low current flowing through the traveler wires and the close proximity of the conductors. However, in certain situations, EMI can be a concern. For example, if the traveler wires are run in close proximity to sensitive electronic equipment, such as audio amplifiers or computer networks, EMI may cause interference. In such cases, it may be necessary to take steps to reduce EMI, such as using shielded cables or adding filters to the circuit. Secondly, let's delve deeper into the role of the neutral wire in electrical circuits. As previously explained, the neutral wire provides a return path for the current to the source, completing the electrical circuit. In a standard 120-volt circuit, the hot wire carries the current to the load, and the neutral wire returns the current to the source. The neutral wire is typically grounded at the service panel, ensuring that it is at or near 0 volts potential relative to ground. This grounding is essential for safety, as it provides a low impedance path for fault current to flow back to the source in the event of a ground fault. Without a properly grounded neutral wire, a ground fault could cause a dangerous voltage to appear on the metal parts of electrical equipment, posing a risk of electric shock. In three-way switch circuits, the neutral wire is connected directly to the lighting fixture, providing the necessary return path for the current when the fixture is energized. The traveler wires do not carry the neutral current, as they simply act as a pathway for the current to be redirected based on the switch positions. Thirdly, let's expand on the discussion of switch loops and their application in electrical wiring. As previously mentioned, a switch loop is a wiring configuration where a switch is used to control a lighting fixture from a single location. In a switch loop, the hot wire is run to the switch, and another wire, called the switch leg, is run from the switch to the lighting fixture. When this switch is closed, it completes the circuit and the fixture turns on. When the switch is open, it breaks the circuit and the fixture turns off. Switch loops are commonly used to control lighting fixtures in rooms, hallways, and other areas where it is desired to have a single switch control the light. Like three-way switch circuits, switch loops do not require a neutral wire at the switch because the switch simply interrupts the flow of current to the fixture. The neutral wire is connected directly to the fixture, providing the return path for the current. Fourthly, let's reiterate the importance of adhering to electrical codes and standards when installing and maintaining electrical systems. The National Electrical Code, NEC, is a comprehensive set of guidelines for safe and effective electrical installations. The NEC is updated every 3 years, and it covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electricians and other electrical professionals to be familiar with the NEC and to follow its guidelines when working on electrical systems. In addition to the NEC, many local jurisdictions have their own electrical codes that must be followed. These local codes may be more stringent than the NEC in some areas, and they may also address specific local conditions or concerns. It is important to check with the local authorities to determine the applicable electrical codes before starting any electrical work. Fifthly, let's emphasize the importance of consulting with a qualified electrician when dealing with electrical systems. Electrical work can be dangerous, and it is important to have the necessary knowledge, skills, and experience to do the work safely and effectively. A qualified electrician has the training and experience to properly install, maintain, and repair electrical systems. They can also help to ensure that the installation complies with all applicable electrical codes and standards. If you are not comfortable working on electrical systems yourself, it is always best to hire a qualified electrician to do the work for you. Sixthly, let's consider some additional factors that may influence the need for a neutral wire in a three-way switch circuit. As previously mentioned, the length of the traveler wires, the type of lighting fixtures being controlled, and the presence of other electrical equipment in the vicinity can all affect the need for a neutral wire. For example, if the traveler wires are very long, the voltage drop in the wires may be significant. This voltage drop can affect the performance of the lighting fixtures, and it may be necessary to use a larger wire size or to install a neutral wire to compensate for the voltage drop. Similarly, if the lighting fixtures being controlled are very sensitive to voltage variations, it may be necessary to install a neutral wire to ensure that the fixtures receive a stable voltage supply. Furthermore, if there is other electrical equipment in the vicinity that is sensitive to EMI, it may be necessary to install a neutral wire to reduce the level of EMI in the circuit. Seventhly, let's reiterate the importance of proper grounding in electrical systems. Grounding is a critical safety feature that helps to protect against electric shock. In a three-way switch circuit, the grounding conductor should be connected to the metal boxes that house the switches and to the metal frame of the lighting fixture. This provides a low impedance path for fault current to flow back to the source in the event of a ground fault. When a ground fault occurs, the fault current will flow through the grounding conductor back to the source, causing the circuit breaker or fuse to trip and energize the circuit. This prevents a dangerous voltage from appearing on the metal parts of electrical equipment, reducing the risk of electric shock. Eighthly, let's discuss some common problems that can occur in three-way switch circuits. One common problem is that the lighting fixture may not turn on or off when the switches are operated. This can be caused by a variety of factors, such as a loose wire, a faulty switch, or a broken wire. Another common problem is that the lighting fixture may flicker or dim. This can be caused by a voltage drop in the traveler wires or by a faulty lighting fixture. If you experience any problems with your three-way switch circuit, it is important to have it checked by a qualified electrician. Ninthly, let's provide some tips for troubleshooting three-way switch circuits. Before troubleshooting a three-way switch circuit, it is important to turn off the power to the circuit at the circuit breaker or fuse box. This will help to prevent electric shock. Once the power is off, you can begin to troubleshoot the circuit. Start by checking the switches to make sure that they are operating properly. Use a multimeter to check the voltage at the switches and at the lighting fixture. If you find any loose wires, tighten them securely. If you find any faulty switches, replace them. If you find any broken wires, repair them. Tenthly, let's emphasize the importance of ongoing maintenance and inspection of electrical systems. Electrical systems should be inspected regularly to ensure that they are in good working order and that they are not posing any safety hazards. Three-way switch circuits are no exception. The switches should be checked to ensure that they are operating properly and that the wires are securely connected. The wiring should also be inspected for any signs of damage or deterioration. If any problems are found, they should be corrected promptly by a qualified electrician. 11thly, let's address the misconception of induced currents in metallic conduits. There's a common idea that running conductors carrying alternating current, AC, through metallic conduits without proper grouping can lead to induced currents in the conduit itself. This is indeed a valid concern. When AC current flows through a conductor, it creates a magnetic field around it. If they are outgoing and return conductors, or in this case, all current-carrying conductors of a circuit, are not grouped together in the same conduit, the magnetic fields they generate do not effectively cancel each other out. This resulting net magnetic fields can then induce a current in the metallic conduit. This induced current has a few undesirable effects. Firstly, it wastes energy because the induced current dissipates energy as heat due to the resistance of the conduit. Secondly, it can cause the conduit to heat up, which can be a fire hazard, especially if the conduit is in contact with combustible materials. Thirdly, it can create a magnetic field outside the conduit, potentially causing interference with nearby electronic devices. The NEC addresses this issue in section 300.20. This section mandates that all phase conductors, the grounded conductor if used, and the equipment grounding conductor, EG, for a circuit must be grouped together in the same raceway or cable. The reason for this requirement is to minimize the magnetic field external to the raceway or cable, thereby reducing the induction of currents in the raceway or surrounding metallic objects. While the initial question references this section, it's important to clarify its relevance to the specific scenario. In the case of the two-wire MC cable used for the travelers, the primary concern isn't about inducing currents in the conduit itself to the extent that it poses a significant hazard. The travelers carry current only intermittently and the current levels are typically relatively low. The major concern is whether the absence of a dedicated equipment grounding conductor EG within the two-wire MC cable creates a safety issue. The MC cable itself, if properly installed with approved connectors, serves as an equipment grounding conductor. However, relying solely on the metallic sheath of the MC cable for grounding over a long distance can be less effective than having a dedicated EGC. A dedicated EGC provides a lower impedance path for fault current, which helps to ensure that overcurrent protective devices, such as circuit breakers, trip quickly in the event of a fault. Now let's discuss the implications of using a 2-wire MC cable for travelers and explore potential solutions. Firstly, it's important to verify that the MC cable is indeed listed and labeled for use as an equipment grounding conductor. The listing information on the cable or its packaging should clearly indicate this. If the MC cable is not listed for grounding, it should not be used for this purpose. Secondly, ensure that the MC cable connectors are properly installed and tightened. Loose connectors can increase the impedance of the grounding path, reducing its effectiveness. Use antioxidant joint compound on the threads of the connectors to prevent corrosion and maintain a low impedance connection. Thirdly, consider the length of the MC cable run. For long runs, the impedance of the metallic sheath can become significant. In such cases, it may be advisable to supplement the grounding path by running a separate equipment grounding conductor alongside the MC cable. Fourthly, if replacing the existing 2-wire MC cable with a 3-wire MC cable is not feasible due to the difficulty of the installation, consider other options for improving the grounding. One option is to install a supplemental grounding electrode system, such as ground rods, near the switch locations. This can help to reduce the ground impedance and improve the overall safety of the electrical system. Another option is to install a ground fault circuit interrupter, GFCI, circuit breaker to protect the circuits. A GFCI breaker will trip if it detects a ground fault, even if the grounding path is not perfect. This can provide an additional layer of protection against electric shock. Now let's summarize the key points and provide some practical recommendations. Travelers in the 3-way switch circuit do not inherently require a neutral conductor. However, it is important to ensure that the installation complies with all applicable electrical codes and standards. The National Electrical Code, NEC, requires that all phase conductors, the grounded conductor, if used, and the equipment grounding conductor, EG, for a circuit must be grouped together in the same raceway or cable. While the 2-wire MC cable used for the travelers may not pose a significant safety risk or EMI concern under normal circumstances, it is important to verify that the MC cable is listed for use as an equipment grounding conductor and that the connectors are properly installed and tightened. For long runs of MC cable, it may be advisable to supplement the grounding path by running a separate equipment grounding conductor alongside the MC cable or by installing a supplemental grounding electrode system. It is always recommended to consult with a qualified electrician to evaluate the specific installation and to verify its compliance with the electrical codes. A qualified electrician can also help to identify any potential safety hazards and to recommend appropriate solutions. Finally, remember that electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself from electric shock. Always turn off the power to the circuit before working on it, and use appropriate safety equipment, such as insulated gloves and tools. If you are not comfortable working on electrical systems yourself, it is always best to hire a qualified electrician to do the work for you. Let's explore the concept of voltage drop in electrical circuits and how it relates to the selection of conductor sizes, especially in the context of long runs such as the 100-foot run of MC cable mentioned. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to the conductor's resistance. When current flows through a conductor, some of the electrical energy is lost as heat due to the resistance of the conductor. This loss of energy results in a decrease in voltage at the load end of the conductor compared to the source end. Excessive voltage drop can have several negative effects. Firstly, it can reduce the performance of electrical equipment. Lighting fixtures may be dimmer, motors may run slower, and heating elements may produce less heat. Secondly, it can cause equipment to malfunction or fail prematurely. Electronic equipment is particularly sensitive to voltage variations, and excessive voltage drop can damage sensitive components. Thirdly, it can waste energy. The energy lost due to voltage drop is converted into heat, which is dissipated into the environment. This wasted energy increases the operating cost of the electrical system. The NEC provides guidelines for limiting voltage drop in branch circuits and feeders. The recommended maximum voltage drop for branch circuits is 3%, and the recommended maximum voltage drop for feeders is 5%. These limits are intended to ensure that electrical equipment operates properly and that energy is not wasted. To calculate voltage drop, you can use the following formula: voltage drop equals to *K I D/Cm, where voltage drop is the voltage drop in volts, K is the DC resistance constant for the conductor material, 12.9 ohms for copper and 21.2 ohms for aluminum, I is the current in amps, D is the one-way distance in feet, and Cm is the circular Mills area of the conductor. The circular Mills area of a conductor is a measure of its cross-sectional area. The larger the circular Mills area, the lower the resistance of the conductor. To use this formula, you need to know the current flowing through the conductor, the distance of the run, and the circular Mills area of the conductor. The current can be determined by dividing the power of the load by the voltage of the circuit. For example, if the load is a 1000 watt lighting fixture and the voltage is 120 volts, the current is 1000/120 equals 8.33 amps. The distance is the length of the conductor run in feet. The circular Mills area of the conductor can be found in the NEC or in conductor manufacturers' catalogs. Once you have these values, you can plug them into the formula to calculate the voltage drop. If the calculated voltage drop exceeds the recommended limits, you need to increase the size of the conductor. Increasing the size of the conductor will decrease its resistance and reduce the voltage drop. Now, let's apply these concepts to the specific scenario of the 100-foot run of MC cable for the travelers. Since the travelers only carry current intermittently, the voltage drop in the travelers is not typically a major concern. However, it is still important to consider the voltage drop to ensure that the switches operate properly. The current flowing through the travelers depends on the load connected to the circuit. In this case, the load is 8 toques for 120 volt fluorescent fixtures. Assuming that each fixture draws approximately 1 amp, the total current flowing through the travelers is approximately 8 amps. Using the voltage drop formula, we can calculate the voltage drop for a 100-foot run of 14 American wire gauge (AUG) copper wire, which has a circular Mills area of 2080. Voltage drop equals to *12.9 100/2080 equals 9.92 volts. This means that the voltage at the switch end of the 100-foot run will be 9.92 volts lower than the voltage at the source end. If the source voltage is 120 volts, the voltage at the switch end will be 110.8 volts. This voltage drop may be acceptable, depending on the type of switches being used. However, if the switches are sensitive to voltage variations, it may be necessary to increase the size of the conductor to reduce the voltage drop. For example, if we use 12 AWG copper wire, which has a circular Mills area of 6530, the voltage drop will be voltage drop equals to *12.9 *100/6530 equals 3.16 volts. This voltage drop is significantly lower than the voltage drop for 14 AWG wire, and it is likely to be acceptable for most switches. In summary, voltage drop is an important consideration when selecting conductor sizes, especially in the context of long runs. It is important to calculate the voltage drop to ensure that it does not exceed the recommended limits. If the calculated voltage drop exceeds the limits, you need to increase the size of the conductor. While the voltage drop in the travelers of a three-way switch circuit may not be a major concern in all cases, it is still important to consider to ensure that the switches operate properly. Always consult with a qualified electrician to determine the appropriate conductor sizes for your specific application. NEC Table 310.15, formerly known as 310.16, deals with the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in various installation conditions. This table is crucial for determining the appropriate conductor size for a given application based on the amount of current it will carry. The ampacity of a conductor is the maximum current, in amps, that the conductor can carry continuously under specified conditions of use without exceeding its temperature rating. The temperature rating of a conductor is the maximum temperature that the conductor's insulation can withstand without deteriorating. The ampacity of a conductor depends on several factors, including the conductor material, copper or aluminum, the conductor size, the insulation type, the ambient temperature, and the number of conductors in a raceway or cable. NEC Table 310.15 provides ampacity values for conductors installed in various conditions, such as in free air, in raceways, and in cables. The table is organized by conductor size, insulation type, and ambient temperature. To use the table, you need to know the conductor size, the insulation type, and the ambient temperature. You also need to know the number of current-carrying conductors in the raceway or cable. If there are more than 3 current-carrying conductors in a raceway or cable, you need to apply a directing factor to the ampacity value from the table. The directing factors are provided in NEC Table 310.15 current. For example, if you have 4 to 6 current-carrying conductors in a raceway, you need to direct the ampacity value by 80%. This means that the ampacity of the conductor is reduced by 20%. The purpose of directing is to prevent the conductors from overheating due to the combined heat generated by all of the conductors in the raceway or cable. In the specific scenario of the 100-foot run of NC cable for the travelers, it is important to consider the ampacity of the conductors to ensure that they are not overloaded. As mentioned earlier, the total current flowing through the travelers is approximately 8 amps. If we are using 14 AWG copper wire with THHN insulation, NEC Table 310.15b16 shows that the ampacity of the wire is 15 amps at an ambient temperature of 30 degrees Celsius. Since the current flowing through the wire is only 8 amps, the wire is not overloaded. However, if the ambient temperature is higher than 30 degrees Celsius, the ampacity of the wire will be reduced. For example, if the ambient temperature is 40 degrees Celsius, the ampacity of the wire is reduced to 13 amps. In this case, the wire is still not overloaded, but it is getting closer to its maximum ampacity. If there are more than 3 current-carrying conductors in the MC cable, we need to apply a directing factor to the ampacity value. Since there are only 2 current-carrying conductors in the MC cable, we do not need to apply a directing factor. In summary, NEC Table 310.15 is a crucial tool for determining the appropriate conductor size for a given application based on the amount of current it will carry. The ampacity of a conductor depends on several factors, including the conductor material, the conductor size, the insulation type, the ambient temperature, and the number of conductors in a raceway or cable. It is important to use NEC Table 310.15 to ensure that the conductors are not overloaded and that the electrical system is safe and reliable. And let's remember that consulting with a qualified electrician can help to ensure that the electrical system complies with all applicable codes and standards and that it is safe for operation.